Good morning, everyone. So I have checked most of the quiz. I think some of you get a perfect score. I haven't checked the average, but I think around maybe around 50 something, the average. So you will see that while a few, maybe not few, some of you get a perfect score or a good score, but some other students, they get really low. So the distributions is equal on the left and right side. So in terms of statistics, not good, not good. I hope the quiz because I took the questions from the typical questions, so I expect that at least you get like you can answer all the questions. I mean, you get the correct concept. Okay? If you have maybe miscalculations in some process, still okay, it's still a good score. But I think almost half is not really understand the question. So I think that's the problem. Okay. Anyway, tomorrow I think I will deliver your quiz. And this is the last week, right? The sequence. So let me just get you into review of what we have done so far. So let's say we are having some sequence. Okay. So your goal is to determine the sequence whether it is converges or diverge. Start with first is that's the first one. The second one. And then the third one. Third one is let me give you a couple minutes, maybe 5 minutes to try and check whether it's converge or diverge. No. Sorry. You're right here. This is A, B. Okay. So three sequence. This is very, very standard sequence, I think. Okay, now if you want to determine the converge diverge sequence, what you're going to do? What should you do?
Take the limit.
Yeah, take the limit. Okay. So you need to remember limit from your calculus 1. So all the property of limit and all the limit knowledge from calculus 1, you're going to use it to determine this problem. Okay. What do you think about the first one? The first sequence? Just looking at the glance, if you know, you can take it like not in a minute, like in a seconds, you know, oh, this will be divergent. Yes, divergent. Okay. Do you know why? You know why? You know why, Gary? No? Okay. This is n to the power of 4, right? It's n to the power of 3. This is faster or increase faster, right? In terms of limit, this goes to be infinite, right? Okay. Or if you want to make it more clear, in the limit, so let me write, and then let's divide all like with the biggest power, right? This is 1, this is 1 over n, this is 2 over and cube. And this will be 1 over 0, which is diverge. Okay? So diverge. Now from the same or similar logic, the second sequence we could get easily that this will prove that n squared, same power. Okay. Not really care much about this square root, right? Because it's going to be the same power, so this should be converged. Okay. But sometimes, if you want to write converge, sometimes you need to determine the value also. Okay. So I think that's one thing. Okay. Unless the question is asking converge or diverge, I think it's still okay. Sometimes you don't really need to calculate what converge, what numbers converge, but sometimes you just write converge or diverge. Okay. But here, I think I will just show you the method. We can think this, and let's say we are going to divide all with n squared. Let's say divide with n squared like that. So we will have, this is 1 over n squared plus 4. This is 1 over n squared plus 1. And if we take the limit, one over n squared becomes 0, right? So this will be 2. So it's converged. Okay, and then what about this third one? How?
Because the bottom one is infinity.
Yes,
And
yes.
the cosine square is
From 0 to 1.
Yeah. Correct. But if you want to make it more clear, you can just simply use the squeeze theorem in limit. And then you can imagine that the cosine squared is maximum value is 1, right? So you could imagine that we could take this
cosine squared n. Let's say this is going to be from 0 to 1, since it's squared, so this is the possible value for the minimum and maximum value. So then, if we take it into divide by 2 over n, so this will happen, right? And then we know that limit Sn going to be infinity of 1 over 2 to the power of n. This is simply saying that 1 over n because it's exponential. So this will be 0. So since limit on the left 0, limit on the right also 0, then the limit in the middle will be 0. So it will be converged. So by squeeze theorem, then limit also 0, so it's converged. Okay, I think that's all the review for the sequence. Maybe later, if we want to have more discussion on sequence, we can have another review. But what I would like to explain for today's class is the next section, which is series. Okay, and sometimes if you are maybe mix between sequence and series, that will be a little bit dangerous. Okay, so you need to really distinguish which one is sequence, which one is series. Okay, now let's move to series. Okay, series. And this is the same Zeno paradoxes that I mentioned at the beginning of the sequence. So using the same paradox, if you would like to total the distance, so total distance, then we could add all the numbers, right? So we could add from half plus 1 over 4 plus 1 over 8 and so on and so forth. And we could write them like this number. And if we take the sum of these infinitely many numbers, it will be equally to, let's say we have 1 meter for the distance. So it should be equal to 1. And if you remember the limit, then this could be true. It could be true. Okay. Well, of course, if you imagine in practice the rules for the distance, the man will not get into the wall, probably, right? But in terms of limit, we could ignore some smallest number between the gap between the man and the wall. That's the limit concept. And because of that, we could approach or approximate it, it will be equaling to 1, right? And then if we also look another example, like in pi, this is pi, and I'm not sure for today's standards, because there are scientists in mathematics sections that they are going to find how many numbers behind the decimals. Okay, so I forgot exactly how many numbers they discovered. What is the number here for pi? But for our course now, what I would like to explain is we could define this number and making into the summations. We could make into summations like this. And this could be, we could imagine this as a series too, right? So if we would like to add like A1 plus A2, A3, A4 until some AN, we call this is an infinite series. Or just a series, that's still okay. And we write this as a sum, or we simply just write just sum of AN. Okay, but now if we imagine like we have a really random number from let's say it's like 1 to 10 or 1 to infinite number. So if you add 1 plus 2 plus 3 plus until n, and we don't know n how many will end, we could see that the trend is increasing larger and larger, and we are not having any bounded value, right? So it's getting larger, it's getting infinite. But if we think like maybe in a Zeno, like this one, or high, they turns out to be a value, right? You can find pi from this sequence as summation of sequence, or you could find value 1 from this half 1/4, and you sum all of the numbers, okay? So there would be some rules to make the series converge, okay? So it seems reasonable for the Zeno, if we write the Zeno as a sum, and if we add all, and this will be equal to 1. Now, one way to see this could be true is by taking the partial sums. By taking the partial sums, let me maybe move this a little bit lower. So consider partial sum. Now the partial sums is we are going to, let's say you have A1 until AN. What partial sums doing is we are going to split this sequence. So we are going to take, let's say A1 is S1. Let me just write here. So we could take the S1 as A1, and then take S2 as A1 plus A2, S3 is A1 plus A2 plus A3, and so forth. So we could take the Sn, right? We could take this is A1 plus A2 plus A3 plus An, and we could write down the sum. Let me write this a little bit left. So we could write this is as a sum of AI, like that. now we could take some definition from this, all of this. Okay. So if we take the series, let's say we have a sum of an, and it's equal a1 plus a2 plus a3 and plus dot dot dot, and then we could write the partial sum as Sn, okay? And then if, okay, this is really important here. So if the sequence is convergent for the Sn, okay, and limit Sn approaching infinity of Sn equal S, which means its limit exists as a real number, then the series, okay, the series of sum an is called convergent. Okay. So okay, we can write that a1 plus a2 plus an is equal S, or we could write the sum of an will be equal to S. This S is what we call the sum of the series. Okay. If the sequence is divergent, the sequence of the Sn divergent, then the series is called divergent. Okay. So we need to describe first that the sequence, okay, the sequence of this Sn, we need to know that it is convergent. Okay? And then we take the limit, it exists, then we could write the convergence of this series. Okay. Okay. Now let's look back here. Let me explain a little bit here. So at the beginning of the sequence, we know that the sequence, before we add with plus like this, with the sequence itself is convergent, right? We know from the early introductions. Okay. Now if we plus this, we get the value 1. Okay. This is what it says. So then, this is what the definition is. Okay. So you can remember the Zeno paradox, okay? If you want to make it in more visuals. So you need to take the sequence, okay? Take the sequence, make sure you know the sequence is convergent, okay? And then you will know that perhaps the series will also converge. So you need to know the sequence itself is converged. If we are given, for example, let's say we have Sn, let's say we have this is our Sn, okay. Now the sum an is the limit of the partial sum, or we could just input the value and we could compute the limit. If you see here, we could directly write that this is 2/3. Okay. Okay, now let's start with this. Okay, we have the series sum. Okay, from n equal 1 to infinity, 1 over n multiply with n plus 1. Okay, for the to begin this conclusions, we could write the sum of the n. We could try sum of the n. Try n equal 1, 2, 3, and etc. You'll see some interesting numbers. But perhaps let me write like Sn. We could also write in terms of Sn that this is going to be. Let me write with another variable I. Okay. To make differences with the original sum. So I plus 1. Okay. So if we take equal 1, so 1 plus 1 is 2, so it will be 1 multiplied by 2. Okay, I will write in terms of this multiplications, okay, to see whether we have some patterns. Because if we multiply just as it is, maybe we are not going to see the patterns. And then plus, let's try 2. So let's try 2. 2 plus 1 is 3. So it's supposed to be 2 multiplied by 3. Okay. And then you could take another one. It's 3 multiplied by 4. Okay. And then you will see all the numbers left. Let me just make a conclusions that this will be n plus 1. Okay. Okay, now perhaps we could simplify these terms. Okay, so let me write in the just. Okay, so take partial fractions. Do you remember partial fractions? So anyway, that the idea is to separate the denominator. Okay, so we have I plus and then take A or B like that. Okay, and then in a short summary, skip some process. Let me simplify this, and this become 1 over I minus 1 over I plus 1. Okay. If you are maybe not sure on partial fraction, check. I think in calculus 1 should be still fresh. It's near the end of the chapter, last chapter. Okay. So now this sum for this I plus 1, we could write in terms of we decompose the fractions. Okay? We can write in terms of this 1 over I minus 1 over I plus 1. Okay, and then let's see whether we could have more simplified patterns. Okay, so let's try from I equal 1. Okay, so this will be 1 minus half, right? That's it for the first term. And then plus the second term, we take 2, 1 over 2 minus 1 over 3. Okay? And then take another addition. This is 1 over 3 minus 1 over 4. Okay, you'll see the pattern. See the pattern? Half, cancelling, right? 1 over 3, 1 over 3 cancels, right? And you could imagine that we are going to calculate until some n, right? So we are going to see that at the end of the day, we're going to plus 1 over n minus 1 over n minus 1. And all the terms in between will be cancelling out. So this negative half plus half, 3, and 1 over 4 sometimes somewhere in the middle. And of course, this will be also cancelling.
That not 1 over n plus 1.
Hmm?
That's 1 over n plus 1.
Oh, yeah. Why I write minus? Okay, so cancelling. So then, finally, we got a conclusion that this will be 1 minus 1 over n plus 1. In which we could take the limit as n approaching infinity of 1 minus 1 over n plus 1. This will be equal to 1. Let's say 1 minus 0, or just 1. So this will be giving you the conclusion that this series is converged. Let me write a little bit in the middle here. Okay. So this is what we call, what we have here, this pattern here, this is what we call the telescoping sum. So sometimes this method really good to show the pattern of the series. So the idea, you know, the telescope, what telescope does, you zoom in something, right? You see something to zoom in. This is like a zoom, you are zooming to some numbers. So the idea is you are going to sandwich all the numbers, and all the numbers in between will cancel. Okay. Perhaps in another series, it's not exactly like this. Maybe the canceling part will be here and here and here and here. This is also considered as a telescoping sum also. Not only canceling the numbers like after and before. Okay. It can be also another series, the canceling from here to here, here, okay. That means that sometimes maybe if you think that it could be work in telescoping sum, you need to try several few terms. Maybe try 1, 2, 3, 4, see the terms. If you see, oh, maybe this will be cancelling out, and you can simply make some conclusions about your series. Okay, but the interesting fact on this series, okay, we know from the telescoping sum, the series will be converged. But if we would like to know the sequence itself. Let's say we want to take the limit of this. This is going to be what we could write. This is going to be 1. So this is going to be 0, right? Okay, this is going to be 0, right? But if we take this as a series, if we make this as a series, it will be 1. Okay? And it will be an interesting fact. So if we would like to then make into the graph, okay, this is what the sequence will be. Take it into 0. And the Sn, the sequence itself for Sn is going to be 1, right? So the series is 1, the sequence is 0, okay? So this is make a new foundations for our understanding. So later we are going to see that if the series is converged, or if we if the limit of the sequence is 0 and the series is converged, or if the series is converged, then the conclusion, the limit should be 0. Okay? The limit of this sequence is 0. Okay? But before that, let me go through several few series before that. Okay, so this is the telescoping sum. Okay, telescoping sum. Okay, any questions on this? Okay, I think we can move on. So this is sequence. Limit sequence is 0. This is, we have done this before. Wait a minute. This is done. Okay, we start from another point of view, what we call the geometric series. Geometric series, another series that are I think very basic. If you learn sequence and series before, this should be one of the series that I think quite a lot in probably in your high school. So to start with, the geometric series start with the first term A, and then we have a ratio R that is going to multiply with this the first term to make a second term, and then for the third term we are going to have another R multiplied, and goes on until sum n minus 1, like that. Okay. And we could take this in a sum, and then we need to make sure that A is not equal to 0, and R we call as a common ratio. if we remember the Zeno paradox, this is start from half, right? We could say that this is also a geometric. So it starts from half A, and R is half. Okay. And we could write the partial sum. We could write Sn as A plus AR plus AR squared plus AR cubed plus plus AR n minus 1. Okay. To get the sum formula for geometry, okay, this is usually what we do. We multiply Sn with R. Okay. So all the things inside will be multiplied with R. Okay. So let me write a little bit to the left. So A becomes AR plus AR squared plus AR cubed plus AR4 plus this becomes AR n minus 1 and plus AR n. Okay, so we multiply with R, and then what we are going to do is we are going to subtract. Okay, so all the terms inside in between A and the first and the last term will be cancelling. Okay, and then we could get Sn minus Rsn is A minus AR with power of n. Okay. And then this will be Sn. We could derive the formula. This is A 1 minus R with power of n over 1 minus R. Okay. Very interesting way to get the result, right? I believe this is first done by Gauss, and the same Gauss who invented the matrix, and the same Gauss who invented the magnets. He's doing this when he was still elementary school. Yeah. Okay, I think we will take a break. Okay, let's continue for a while. So this is the geometric series, and this is how usually we take the formulation for the Sn for the partial sums. If you see we have R with power of n. If you remember, with this R of n, we could have some rules, okay? And we could make this if we take the limit. If you take the limit Sn approaching infinity of the Sn, then we could take this. Let me divide, becomes two separate expressions. So this is the first expression, and the second one is A 1 minus R, and then multiply with R with power of n. Okay. And we could take the A 1 minus R factor out, or we take this is going to be, because this is a constant, right? This is a constant. And we could focus the limit only with R power of n. Okay. So from the previous examples or previous in sequence, I think we mentioned that if we take the Rn, okay, this will be going to be, or maybe let me write here, if R is between -1 until 1, then R power of n will approaching 0 as n approaching infinity. Okay. Or if not, we could take just like a limit as usual. We define with R power of n, define what R power of n, define all, and this will be equal to 0, okay, because this will get an infinite, and this will be constant over infinite, this will be 0. We could think like that. Or if you remember the last time, we make some rules regarding this R with power of n, and we say that the R should be in between -1 to 1 to make it 0. Okay? So that's why the Sn so the sum let me write here. So this is the conclusions. Let me write conclusion here. Okay. So geometric series. This is convergent if R absolute value is less than 1, which means we need to have our fractions. And the sum is okay. If the ratio is greater or equal 1, the series is divergent. That's the conclusions. Okay. That's why in Zeno paradox, we get A is half, R is half. So half defined 1 minus half is half, so half is 1. So that's the Zeno, if we remember the Zeno paradox. So if you could identify the series as a geometric series, meaning you could make it in this component, then we could directly use these formulations. Okay? Make sure that the R is less than 1. Okay? And we could compute the value. And then try the left question. 5 minus 10 over 3 plus 20 over 9 minus 40 over 27. Okay, so if we look at the question on the left, we see that the first term is the a is 5, right? And since it's already make some information on the geometric, so it's supposed to be geometric. So 5 becomes 10 over 3, 20 over 9, and we see that this is going to be multiplied with a negative 2 over 3, right? So the r is negative 2 over 3. Okay. So the series we could write as 5, negative 2 over 3, and minus 1. Okay, that's the series. And since the ratio is less than 1, or in absolute value, which means that the sum this is the first term, the 5, 1 minus the ratio, so 5 minus 5 over 3 is 3. If we look closely, if we look at the graph, if you take for some n equal 1, and then 2, 3, 4, we can see that this is going to be having some oscillations, okay? But then it's going to be bounded to this number 3, okay, as we see at the result for the sum. Okay, from this geometric, we could also consider, if we want to make another conclusions, let's say we have an x with power of n, and we say that the absolute value of x itself is less than 1. Okay? And we could consider this x with power of n as a geometric as well. Okay, so we can see that this is going to be, if we take the terms one by one, we take 1 plus x squared plus x cubed plus dot dot dot, right? You see the ratio itself, it's x. Okay, so this is geometric. Okay, with a is 1 and r is x. So we could take the summations as 1 over 1 minus x. And this will be very important in later sections, which we call the power series. So whenever you know that it's supposed to correlates with the geometric series, which the ratio is less than 1, and you have this x to the power of n. We could take that into our 1 over 1 minus x, okay, as its sum. Okay, its sum. Okay. Now, one main idea on this series. Okay, we call the idea is the divergence test. But before that, let's see this one first. So this idea called the divergence test. So, in your textbook, in example 8, there is a question: show that the harmonic series, the sum of 1 over n, 1 plus half plus 1 over 3 plus dot dot dot, is divergent. Okay. What we are going to do is, we are going to focus, okay, consider the partial sums for S2, S4, S8, S16 and S32. Okay. Why these particular partial sums? Because you can see with the numbers when we grouping all the numbers together, and we could see how it looks like later. So let me just take this. This is in your textbook. If you have the textbook, you can see on the example 8. So let's say we define all the terms, especially for S2, S4, S8, and so on. So S2, 1 plus half from the harmonic series, and then for S4 is 1 plus half plus 1 over 3 plus 1 over 4. Okay, and then from this conclusions, we know that this is going to be larger than, let's say, if we take this 1 over 4. If we change the 1 over 3 to 1 over 4, of course, if we want this is greater, right? So we could imagine this is, we can imagine the value itself, right? And then the 8 on 8, we take all terms until 1 over 8, okay? And then we compare with another term, but we change all the 1 over 3 to 1 over 4, all 1 over 5, 6, 7 to 1 over 8. Okay. This is to show that this is going to be really large compared with this one. Okay. And we could plus this, because it's easy to compute, that is half, and this is going to be 1 over 4, 1 over 4, this is going to be half, another half. So 1 plus half plus half plus half. Okay. It's going to be 1 plus 3 over 2. The same thing, like S16, and if you want, you could check also the S32. What we are going to do here, we are going to make this as a conclusions that since we take, you see that it's going to be 1 plus 2 over 2, and then 1 plus 3 over 2 for S8, and S16, 1 plus 4 over 2. With the same method, if we multiply the terms, we could see that this is going to be 1 plus 5 over 2, and if we make it this, multiply the term, we could get 1 plus 6 over 2, okay? And then if you take the general term, okay, we take the x with the exponential 2 to the power of n. This is going to be larger than 1 plus n over 2, which means that the harmonic series will be larger and larger, and it is going to be larger than this number here. We approach with this 1 plus n over 2. So if n is getting infinity, then it's going to be divergent. Okay? So as n going to be infinity, Sn is going to be divergent. Or you could say the infinity. Or maybe write S2n first. Okay? And so the Sn is divergent. So therefore, the harmonic series is divergent. So harmonic series is divergent. Well, the method to solve this, you see the method is pretty unusual method, but I think it works. And it's with the help of the changing some terms, okay, especially with the multiplied, the exponential 2, right? The 2, 4, 8, 16, 32, 64. Now this led to the one important theory, and that is the first theory is, this is related to our previous examples. So if the series is convergent, then the limit is equal to 0. Okay. So if the series sum of an is converged, then the limit of the sequence of the an is 0. Okay, the important one, do not reverse the theorem. Okay. This will be really confusing if you do that. So let me write here. So if we start from the limit first, this is will getting, we cannot conclude let me write with the red line here. This is very important. So first you need to know the series need to be converged first. Then you can have a conclusion that the limit will be equal to 0. Okay. So we could start, if you want to prove this theorem, we could start from Sn. We define Sn. Okay, and we could make another relations, okay, between An and Sn, in which An is Sn minus Sn minus 1. So it's the difference between the Sn itself. Okay. So if the sum of An is converged, then the sequence of Sn is convergent. And if you let the limit of Sn is, we could have a value of S, okay. Then since the n minus 1, if we take this infinity as n approaching infinity as well, we will have limit also going to be S. So that's why the limit of an is limit of the difference between the Sn minus Sn minus 1, which is S minus S, which is 0. Okay, maybe to make some intuitive corrections for this theorem. Okay. Remember what we did, the harmonic series, 1 over n? The limit is 0, right? But it's divergent. It's divergent, but if you see the 1 over n, the limit of the sequence is 0. So this is why important. If the limit is 0, we are not sure whether it's converged or diverged. So we need to take another steps to make sure whether it's converged or diverged. But if it is converged, for sure the limit will be 0. Okay. Okay. But then, if we take another approach with limit, if limit has a value or is not equal to 0, if limit is not equal to 0, then the sum is divergent. We can make those conclusions as now as well. Okay, let me write. I think I need to write in a new page. Maybe let me give you an idea. This is one example, the harmonic series. The limit is 0, but the sum is divergent. Okay, now let's take another steps. Now we take the second theorem which we call the test for divergence. This is so in the chapter series or the sequence series, especially for series, we are going to talk more on how to test the series, whether it's converge or diverge. So the first test we call the divergence test. Okay? And another section on the chapter will be more discussion on another test. Okay? So this is the first test. So the first test, it says that if the limit doesn't exist or the limit is not equal to 0, okay, we could take the series directly, make the conclusion that it will be divergent. Okay? Remember, if you have limit 0, you cannot conclude. Okay, you cannot conclude that it's that converge. You need to make sure it's converged, then you make conclusion it's 0 limit. Okay? And then second one, if limit is definitely is not 0 or doesn't exist, then you could say it's diverged. Okay? So now, if you have a series, the first test you can do is take the limit. If it's not 0, you could just answer, okay, it's divergent. So if we have, let's say, example here. Okay. So if we have this series now, so sum n squared over 5n squared plus 4. Okay. We take the limit of the sequence, right? We take the limit of the sequence. And we see that it's n squared, supposed to be have a value, right? So 1 over 5, right? 1 over 5. It's not 0. So this series is diverged. Directly we can make those conclusions. So first check with the limit. So it's not equal 0, right? So we say by the divergence test, the series is divergent. Okay. Okay, if you lost somewhere in the middle of our lecture, the previous page, that's okay. Just remember this one. Okay? Just remember this one. I think the previous one you will be like confusing and lost, but remember this one. Okay? Really important. Even though maybe you're not understanding at the first glance, okay, but please remember this. Okay, just remember this. Very important to identify the divergences. Okay, one more section to end this course is the property. Okay. So property of convergent series. Okay. I think it's pretty intuitive, like a limit. You can imagine this like a limit. Okay. So the next sections we are going to focus on the test for the series. Okay. How to test the series. So first test is divergence test. The next test is, we call it integration test. And then comparison test, limit comparison, and so on and so on. So hopefully tomorrow we could, I think maybe 2 or 3 tests tomorrow, and finishing half of the chapter next week, or probably maybe 70 or 80% next week. So when we finish chapter 11, that will be the content for the midterm. So 10, 11. Okay, I hope we have sufficient time. But I think we can adjust the schedule when we will have the midterm. 8, I think it will be considered in 10, because 10 consider they have the arc length and the surface, so you could focus on that. Okay, any questions? No. Okay, what do you think about the first quiz? Questions okay or not? Yeah, I think if you are aware of how to take like how to be focused, how to be more focused, I think that is the really important, because nowadays you could get any information from internet, right? You could ask the ChatGPT, and if you like in some company they already have like positions for the prompt engineer, the engineer who understand how to interact with the robot, right? How the AI. I mean, you could take all the information for free, but the difficulty is you will have a really hard time to be a focused person, or you will be really having a difficult time to analyze some problem. Because you could get anything, right? You get more information from the website. Then because there's a lot of information, how to filter that is really difficult. Okay, if I'm in your positions, I understand that easily, because I think like 10 or 15 years ago, the technology is not as much as increasing as now. Today is like the internet is getting faster and faster, right? 5G and then maybe 6G in the process, and then we have the AI and so forth, right? So I think the first thing you need to do is try to be more focused. Okay? There's a plenty method to take, but choose which one is suitable for you. Okay? Choose which one is suitable for you. I don't encourage like more practice, more research, no, because every person has a different either ability, either how they perceive their knowledge. They have difference. Okay? It's not a matter of like, oh, this person is smart, this person is not smart. No. That's not the whole point. The whole point is everyone is different, and you have unique ability to learn, okay? And you need to find that by yourself. Okay? I cannot teach you how to learn. You need to find it by yourself. Okay? If you can like take more learning by reading, then try it. If you take learning by writing something, try it. But the more you involve with, like, you need to be there. You need to be like, if you want to focus, you need to be in that positions where all this content is relevant for you. If you think that all this thing is not relevant, all the things you learn will not be sufficient, and you will still like, I still don't understand this, I still don't understand that, because you are not there. That's the important thing. Like, I think more people will be aware of, like, be mindful. You need to have a mindfulness. That's really important. And to get there, you need to find your own way. I cannot teach you how to do that. Like, practice maybe not really working. Maybe if you are not really like find your way to go there. Okay? So be mindful. Okay, be mindful. Okay, I think that's the end of our lecture, and we are going to go to the feedback as usual. So, take this. Okay, this will be about the sequence, okay? To see your feedbacks on sequence. And I hope, as usual, the platform says that you need to be engaged with the website as always. If you put your phone and maybe it has automatically idle the system, it will the platform will confirm, oh, this is disconnected, and that's why everyone was voted. So I'm not sure what, maybe they changed how the server is in the system. I'm not sure why. Okay, I think we can start. Start by feedback on quiz 1. Okay, anything. If you think that is super difficult, let me know. Okay, that is, I think from 3 questions, 2 questions is really, I think this really the simplest one. I think the only difficult one is the number 2. Number 1 and number 3 is supposed to be okay. It's okay, just right, not bad. Okay, difficult. I'm using Indonesian word there. Okay. Calculator. Yeah. Yesterday quiz, no need for calculator. They are. You just need to have like a basic mathematics. Basic mathematics. Okay. Do not rely too much on computer or robots or AI, unless you will be invaded by AI, like in Terminator. Okay. Intermediate. Okay. Easy to understand. That's good. Okay. Okay. If you think that is still too difficult, then perhaps the whole content, you're not really absorbing much information from that. Okay? I'm not like judging you, but maybe you need to find your learning system. Okay, you need to find how to learn. Okay. I think I can skip this. Okay, prepare the first question. Okay, I also forgot which question I make. I think just a convert divergence thing. Quick. Only 40 seconds. 40 seconds. Okay. Remember, you can do this on your mind. Okay? You can do this on your mind. Look at the At the power, look at the power. Look at the power. Okay, are the 30 students submitted? Okay, everyone responded. I think it's okay. Okay, good. Okay. Because the power on the top is greater than the power on the bottom, right? So it should be divergent. Who is 006? Okay, okay. Oh, really tight scores. Okay, the second question, get ready. Okay, let's start. The same questions, but you need to write. If it's diverse, write DID. If you converge, compute the value. Well, I think you know how this is going to be n, and you need to see how this is going to be looks like. Do not be intimidated by the negative. Remember, you can take the limit of this value, right? So you can answer directly also, like the previous question. Okay, 16 submitted. Okay, 18. Okay, this is just a quick question, just to check. Okay, 30. Who's still computing? Okay, you can take the absolute value and take the limit. So it should be 0, right? 1 over infinity. Okay. I think still the same. Yeah, same leader. Okay, congratulations. Congratulations. Okay, and then this will be the your attendance, and also if you have any feedback. How about your TA? Okay, fine. You get to have like a small quiz in TA, right? But every 2 weeks, right? Every 2 weeks. Right? This week? Oh, okay. Okay, so that will be the end of our course.